You start? Okay. Kia ora everyone, good morning. And firstly, thank you so much for making the time to come to this webinar. We'll just get the slide pack started. Thanks, Sina. So I'm Sheila Matthews, and I manage the Future Security and Resilience team here at the Electricity Authority, Te Manahiko. And with me today to present, I have Nasser Faruqi. He's Principal Advisor in my team. And we also have Professor Neville Watson from the University of Canterbury. Welcome, Neville. Thank you so much for joining us remotely. He couldn't make it here physically. A lot of you will probably already be aware or know who Neville is. He is an expert in the field of power quality, and we've had been able to have his support in putting this paper together. So what we do intend to cover today, before that, Neville's actually put in a whole slide pack on harmonics. We won't be able to go through the whole slide pack, but Neville will talk to some of it later in the presentation, and we will upload his presentation as part of these slides when we put it on the website after this presentation. So today we will cover the purpose of today's webinar, the context for this particular consultation paper. I'll talk through about how to make a submission, and then hand over to Nasser. Nasser will give you an overview of the paper, followed by Neville's discussion, and then we'll go into questions from yourselves. So a couple of things around the question and answers. Please pop them into the Q&A function, not the chat function, because we are monitoring the Q&A function. And if for whatever reason we don't get to answer your questions in the time frame, we will definitely get back to you on them. Also, just we've muted the mic, and so it'll just be the Q&A function we are monitoring. And lastly, if you, we are noting the questions today, but if you do want to have it as part of something we need to consider as part of submissions, please do put your submissions in, and I'll talk about that a bit later. So the purpose of today's webinar is to provide you the context for and the purpose of the consultation paper on harmonics, on the governance and management of harmonics. What we did is we've published a suite of papers towards the end of June, on the 25th of June. 4 papers essentially. One is a cover paper, and it gives you the context of what the 3 consultation papers are. 2 of the papers, on the website, if you look at paper 1 and paper 2, paper 1 addresses has options to address frequency issues, and paper 2 has got options to address voltage issues. And I'll talk more about this, but this particular webinar is to discuss the governance and management of harmonics. We did not go to options for this because once Nasser goes through his slides, you'll see that standards regulation is very light in New Zealand. It has not been a big issue in the past. We've had a largely synchronized power system with power flow in one direction, unidirectional power flows, and therefore harmonics hasn't been a big issue in the past. It's very limited and light, and it was too early to go to options. So once we get the submissions, it'll inform the next steps, and we'll see how we go from there. Next slide, please. So the context for this work, we know that there's changes happening to the power system. This is because largely we are moving to a more renewable-based power system. We are replacing our thermal and non-renewable sources of energy with wind, solar, battery, and so on. And they're largely inverter-based resources. With that comes issues, technical challenges for the power system. We get bidirectional power flows. We are getting new technologies onto the system, and the code has been largely written for a synchronous-based system years ago, and doesn't really accommodate these new changing technologies and bidirectional power flows. We also have new participants coming in. We've got consumers. They're becoming prosumers now. They've got solar on their rooftops. They may have batteries, so they have the ability to put power back into the system and not just take off from the power system. We're also going to have to be more reliant now on intermittent and variable sources of generation, wind and solar, and all this together really, affects the security and reliability of the power system. So I just wanted to add here that this is just one of the many projects the authority is working on to ensure we have a reliable power system that during the transition as we go forward. A bit about the Future Security and Resilience, or the FSR work program, which is under which this particular work stream fits in. The purpose of that work stream, or this program, sorry, is to ensure that the power system stays secure and resilient as we put in more and more renewables onto the system and transition to a low emissions economy. So we went out in mid-2022 with a roadmap. It had 10 activities identified in it. We worked with the system operator to put that roadmap together, asking them what are the challenges and opportunities as we transition. So there was a lot in that roadmap. That's also on our website. Also, at the end of the slide pack are links to all the material, relevant material for this work. So yes, we did go in August, publish the roadmap, and then we took it to stakeholders because we needed to prioritize. Obviously, we couldn't do all the work streams, and some of them don't need to be addressed now. It's a 10-year roadmap. So a review of Part 8, the common quality obligations, was flagged as the one that needed to be addressed as soon as possible, immediately, and hence we started the work on that early last year. But also, when we went to stakeholders with this roadmap, they did identify one additional piece of work that needed to be considered, and that was reviewing system operations. So therefore, we got what's the FSO there, which is Future System Operations, which we are reviewing. We did publish a consultation paper on this in Feb, and we are looking at what the next steps will be following submissions we got. So that's aside, so that's our FSO work. And then Part 8, I'll talk about in the next couple of slides. But above that, you see the FSR indicators. And what that is that we published a set of 9 indicators last May. And they're to monitor things that are affecting the power system and potentially would help us prioritize our work streams. So we're monitoring things such as EV uptake in New Zealand, the amount of DER connecting behind the ICPs. We are looking at system inertia. So 9 indicators, and we refresh that information or data every 6 months. So we can see whether there's a radical change to something that makes us want to look at another work stream. And that's why that's sitting above. That's what we're using to monitor the changes to the system. Before I go into the Part 8 work, our statutory objective, it is to promote competition and ensure that the power system is reliable and efficient, and that in turn is for the long-term benefit of the consumers. A secondary statutory objective came in 2022, and that was to protect the interests of small business consumers and domestic consumers. But with these 2 statutory objectives, all our work is done to ensure that these statutory objectives are met. And once we go through the slide pack and go through the rest of you'll see why it is really relevant, this review of Part 8, and how it's going to benefit consumers. Because if we don't have settings that are fit for purpose, then you get an inefficient power system, and then that does not benefit consumers. Thank you. So a bit about the project. It's a review of the common quality obligations. And at this point, it's in Part 8 of the code we're looking. Common quality obligations do sit in other parts of the code too, but mostly in Part 8. So we first started with Part 8, and then we will look at the other parts of the code once this part of the work is done. What are common quality obligations? Well, it refers to the elements of the quality of electricity that's conveyed across the power system. And those are elements that cannot be isolated to a technical or commercial entity or a group of participants. Examples of those common quality issues are exactly what's on the right-hand side: frequency, voltage, harmonics. They go right across the power system, so it's common quality. So we published a paper last April. We published it indicating 7 broad issues that we thought were going to be the things we need to address. Submissions were largely agreed with that, and since then we've been working on options. So last year in June, once we had published the issues paper, we put together a technical group called the Common Quality Technical Group, or the CQTG. They comprise of 11 members from across the industry. So we have technical experts from generators, from transmission, both grid owner and the system operator, and from EDBs and suppliers. We also have some consultants who are specialists in these areas. And with those 11 members, we've managed to get through a lot of work, which otherwise we probably would have had to do a number of consultations. So a big thanks to them, to Professor Neville Watson, particularly for harmonics. It's again, like I said, very, very few people, it's very light in regulation and in the code, and there are very few specialists in New Zealand on this topic. So thanks again to Professor Neville, CQTG. We've also worked closely with the EEA. They have, some of you may know, they've published some excellent guidelines on power quality late last year. And we certainly have to work with NDIE and WorkSafe, because once NASA talks on the next part of this presentation, you'll see some of this regulation, or the regulation rather, sits with WorkSafe, so we do need to work with them. We've also looked at what overseas regulators are doing in this area. So what have we done so far for this project? Last year, April, we published the issues paper with the 7 key common quality issues. Late last month, we've published the suite of papers, 4, of which one is a cover paper. And in the 4th quarter of this year, we plan to publish a consultation on some proposed code amendments to address issues 6 and 7. So we consider that some of the issues that have been identified in 6 and 7 are things that can be dealt with sooner rather than later. They are not as controversial that need to go for a full consultation. So we will be putting options for code amendment proposals, and that is expected in the latter half of this year. And a bit about submissions. All the papers have got details on how to provide a submission. So each of the papers have got a number of questions we're seeking feedback on. Please do give your feedback. And the format is in the papers. The email that you need to send it is also in the papers. It is fsr@ea.gov.nz. Submissions close on the 20th of August. So yes, please do put in your submissions. And prior to that, if you want to catch up with us, if you want to have another briefing, you have any questions at all, either before or after submissions close, please do feel free to get in touch with us. So now I will hand over to Nasa to give you an overview of the paper. Over to you, Nasa.
Thank you, Sheila. Assalamu alaikum and kia ora. Thanks for joining us. Let's discuss the governance and management of harmonics in New Zealand's power system. And just as a primer, if you search for harmonics in our grid code, you can find 3 instances where it has been mentioned, compared to 150 plus pages in UK and likes in the Australia as well. So let's get into it. So what are harmonics? So harmonics are waveforms, which are, our intention is to provide sinusoidal and perfect voltage and current waveforms, but because of non-linearities in the system, switching and other characteristics, we do have non-linear waveforms in terms of voltage and currents, and that forms harmonics. So apart from 50 hertz, which is sinusoidal, we have superimposed waveforms of 100 and even towards 5000 hertz on top of that. Next slide, please. Some of the common sources of harmonics existing are coming from transformers, which happens during energization. We have industrial loads like arc welders, furnaces, ballast, we have rectifiers, and at residential levels, we have computers, switching devices, drives, and also the big ones on the network side is the capacitor banks. So these were all the ones that have been common sources of harmonics, but things are changing a bit fast in the coming years. So when we go to the store, if we get buy one, get one free, we might be happy. But if we get 50 hertz current, but we have superimposed hundreds of harmonics on top of that, it's not a good thing for the power system. It leads to poor power quality. It causes heat. And also in many cases, if the distribution utility assumes that a transformer might last for 20 years in the amp, it might fail or it might get damaged within 10 years. And one of those reasons might be because of harmonics. And it also damages the loads from the consumer sides and also on the data centers. So we don't want to have these harmonics. We can only manage it. We cannot avoid it. And then, apart from what has been, what we have been having as harmonics in the past few decades, we have changed in the power systems. We have more of inverter-based generations. We have more load controllers. We have EV controllers. Now, all these are based on power electronics. And as you can understand, power electronics have got switching devices. And because of these switching devices, they do cause more, they inject more, maybe more harmonics, or they might change the resonance in the system. They might change the network impedances. And the existing harmonics, background harmonics, can actually cause harm to the solar farms or even inverter-based system because they can play around with the PLL, the phase lock loops, and you may not have good power quality of supply from those inverter-based resources, which causes more threat to the system security and reliability. So now let's look at the governance of harmonics. What's there in New Zealand and what's the status quo? The one that we have now has been around for a while from 90s, but this has come from 1960s. UK has been pioneer in managing the harmonics. It was back in 1960s that they got something called G5, which is the grid code for harmonics, and they set the limits, basic harmonic standards, and that was adopted in UK in 1976. And these levels were standardized in New Zealand, and that is what has been taken in the NZECP 36 1993. This was standardized in New Zealand, and now this sits with WorkSafe, which is under MB. There are two issues basically with the governance of harmonics. The first thing, like I said, is that these values and the limits are based on the measurements that was done in 1960s and 70s. So these are basically caused by the HVDC, the motors, and the other loads that were back then, and the generators. So these are a bit outdated. For now, we have more inverter-based resources like solar farm, wind farms, and BESS. So they may not be fit for that purpose. The second key thing is the ambiguity and the applicability of the harmonic standards. So NZECP 36 is the primary standard that is used across several utilities in New Zealand. If they adhere or comply with the code, they do comply with the safety regulations, which is NZECP, because the code is subordinate to the safety regulation. But this, at present, there's no conflict. But the issue comes at how the user interprets it. What we have found from one-on-one engagements with industry stakeholder engagement is that some of the utilities are using NZECP to allocate harmonic limits to the generators as well, whereas the NZECP clearly states it's only meant for loads. We do not have anything specific for the generators. And the other issue is, apart from NZECP, there are some utilities that do follow AS/NZS 61000, or they might find IEEE 513 standards because it is there in part of the transmission code agreement. Now, these standards are very different, and what we have found is that recently, the issue, it doesn't come from a single source. If there are interaction between neighboring solar farms or BESS, there might be a resonance or different impedances at the remote node. So this is a big issue, and we need to have a uniform kind of whole of the system approach to address this. So like I said, there's scattered regulation around. Some utilities might use NZECP 36 even for the generators. There might be some who are using 61000 and some using, sorry, I correct myself, it's IEEE 519. So this was taken, and the thing with IEC 61000, it has been updating quite a lot. They have been keeping up to date with the changes in the power system, the kind of assets that are there in the power system, and also they're trying to address issues that are emerging because of the inverter-based system, solar farms like interharmonics and the likes. So they have changed these values. They might have been from one of the journal paper. And you can see there's a discrepancy. If a utility uses IEEE 519 and the neighboring utility uses 61000, there's already a discrepancy in the harmonic order. So as a solar farm goes and connects to one of the utility, they might have a different set of regulations the other one will have a different set of regulations. So we do have a scattered regulation. So we are trying to bring whole of the system under a single umbrella now. This paper focuses on a very high level. We're not going into too much detail on the operations. We would like to know how it will be evolve into a code. So we have to look at what is the harmonic governance, what is the management of harmonics, and within the management, we have to talk about the allocation and the mitigation principles. First, with the harmonic governance, we have discussed what are the limitations of NZ-ECP 36. And as you can see, it was last updated in 1993. So that is one of the biggest limitations. So we discussed about it. Then we talk about the applicability of AS/NZS 61000 suite of standards. And the reason for that is we have AS/NZS 61000 being adopted by some of the utilities as part of PQ power quality guidelines from EEA published in 2012 and also this year, and also the other regulations like UK, they use it quite extensively in form of IEC 61000. Then we also look about the consideration for other standards and also approaches, because in New Zealand, we do not have to go with a single approach. We can have a hybrid approach. We can look at what are the shortcomings in each of these regulations. We can look at what are the benefits, and then what will be more suitable for New Zealand, because it all depends upon the portfolio of generation that you have, portfolio of assets that you have, and the skinny nature of New Zealand power systems that we have, and the way it is governed currently. So we have to consider all of this. So we are going to look at the governance at a very high level, and then we move on to the harmonic management. And now this is a very key thing, because like I said, if you type in harmonics in our grid code, you have only 3 instances which doesn't talk of any of these things, and this is very important. We need to understand the roles and responsibilities. Like I said, you can have solar farms or even different loads interacting and can cause harmonics in a very remote node. So we have to know which entity will be responsible for those identification, for mitigation, or whatever the reason. We need to define what are the roles of different entities, what are the responsibilities of measurement, of identification, mitigation, and things like that. And the next key thing that we would like to discuss in this paper is harmonics measurement. Overseas, they have been, for the past 2 decades, they have good measurements. It is mandatory in the code, because of which they have got the background measurements. So even before a new solar farms or a BESS or any new asset like a data center comes in, we can understand what is the existing harmonics, and then only we can see that if a new asset is being connected, how that harmonic will be distorted, will it be amplified or otherwise. So having a harmonic measurement is key thing, and there are several things that we need to discuss within the harmonic measurement, like what is the type of aggregation level that you need to have, what are the standards that will go into the harmonics. So that's why we are trying to keep this in a very high level. What is available in New Zealand, what is being done, because elsewhere, here in New Zealand, we can measure up to 2500 hertz, but now because of inverter-based systems, some of the utilities overseas have gone to even 5000 hertz, because these solar farms, they're having issues at more than 4000 hertz. So that's on the harmonic measurement. The other thing is on the planning and compatibility levels. We are trying to understand what is the planning and compatibility levels that we need to have as the whole of the system approach, and not on region by region basis. We have discussed about that, and having that would be quite useful for us to go forward. The next thing is on the voltage levels. We need to define the voltage levels as well, because more than the capacity levels, it is the voltage levels at which you have demarcation of the different utilities. So we need to understand at what voltage levels do we need to impose or have some kind of code around that. And then the most important part that keeps coming up when we had the stakeholder engagement is on the compliance timeframes. For example, if there's a harmonic distortion, and if you want to mitigate it, if you want to procure any of those things, it's a long lead time. And also suppose if the studies are required or if more theoretical work is required, it is a long time frame. So what is the kind of time frame that has to be there, or do we really need that? So we are trying to just have an open discussion. It's like an open canvas. We're trying to have this discussion with the industry to understand, is it possible to have a fixed time frame, so will it be flexible, and what will be the implications of those things? And finally, we have discussed about the harmonic allocation and mitigation principles. So we have looked at what is the status quo on the harmonic allocation, because again, it is not an exact science. Harmonics is not like voltage and frequency where you can have exact science. If it goes below particular threshold, you can have different values. Here for the allocation in US, they go for IEEE standard, which just gives 1/3 of the allocation to the first come first served basis. We have other methodologies as well. We have discussed what is currently being done within the industry, right from top level, from generation, transmission, and distribution. Then we have talked about the AS-NZS based stage-wise approach. This has been taken from IEC 61000, adopted for New Zealand standard. So that's why it is NZS 61000. It is a stage-wise approach, and this has also been advocated in Power Quality Guideline, both published in 2012 and also this year. And this has been adopted by some of the utilities in New Zealand. We have also looked at other approaches because, like I said, we don't have to go fixed with one approach. We can have a hybrid approach for New Zealand, depending upon what is best fit for New Zealand's power system. And also Professor Neville Watson, he has given a lot of anecdotes of how in New Zealand we have different methodologies where we can change the phases to make sure that we have diversities and we can mitigate it. So those are operational part of it. So we have touched upon that. What are the different approaches that we can use for harmonic allocation and mitigation? So this is the overall framework. And now I would like to invite Professor Neville Watson, who has been quite pioneer in power quality. We can have some Kiwi ingenuity here. Professor Neville Watson, we like to discuss regarding this, the emission levels and the disturbance level and the understanding of the utilities on current and voltages of how it goes.
Thank you, Nasser, and thank you for the introduction, Sheila, also. Yeah, I would like to just discuss this as a starting point, because the one thing we have to realize is it's the harmonic voltage that interferes with equipment connected. It's how far away the voltage is distorted from the ideal sine wave. However, the way we actually limit the distortion is the emission levels, and the emission is the current waveforms that either a load or a generator draws through the system. And of course, the thing that connects them together is the system impedance at that frequency. So that basically means if the system impedance is high, you can only allow a smaller harmonic current to flow to reach a given level of harmonic voltage. So that basically means that different parts of the system are going to have different allocations. So there's no possibility to have one level of harmonic current that's applicable to everywhere in the power system. It has to be based on the system impedance. Another way of saying it, it depends on how strong the system is, how easily is the voltage distorted by a current injection. Now, once you get that to that point, at a given point, there's a given harmonic current that can be allowed into the system. And the real question is, how do you allocate that to different customers connected to that point in the system? So the thing to keep in mind, what we were controlling is the distortion on the voltage. What our lever is for controlling that is the current injection into the network. And then all the other issues with harmonic filters or phase shifting, that to mitigate it, they come into effectively changing the current injection that the system sees. So in a nutshell, that's basically it.
Thanks, Neville. Thanks. And like I said at the start, this is only one of the pack of slides he's put together, which we will put up on our website. It's just in the interest of time that we have kind of reduced this section. Are there any questions coming in?
At the moment, no questions coming in. So just a reminder, if you have any questions, to pop them into the Q&A. There we go. Let me just go over to that question. 1 second while it loads. I might just get rid of the slides now, if that's okay.
Yeah, I think the next slide is just on the links. Yeah, there we go. So links to relevant documents is also part of the slide pack. Yeah, cool, that's good. Okay.
So we have a question in the chat from Gerard Demler. Why don't we introduce standards here for inverters that they need to be tunable to filter out the harmonic output and any existing background harmonics or code levels?
Right. So like I said, sorry, Professor, I'll just go before for the regulation part of it. This is on the design phase. During the design phase, we can have standards for inverters, so that will only mitigate the harmonics coming at that point of connection. But like I said, the issue with harmonics is not just coming out from one supplier. It can be interaction between other generators and the loads there. And what we're trying to address here is how the network operators and owners can actually manage this harmonics here.
Neville, do you have anything to add to that?
Yes, I would have to say it is actually a fairly complex area that you're touching on. So normally, if I can just say that standards are either of two types. One is actually for installation, and the other one is actually for devices at the device level. So normally, for example, installation like 61036 is actually an installation standard. The idea being is that every bit of equipment in the installation doesn't have to be compliant as long as you mitigate it by diversity or other things so that what you inject into the grid is within your allocation. And the reason for that is you don't want the factories and installations to have lots of very expensive equipment when you could actually mitigate the harmonics in one step. On the other hand, there are device standards, and particularly these apply mainly to domestic and others, where you're not going to basically monitor or check the installation at each house and consider the house each installation. So what you do is you have a minimum device quality. Now, why it also gets more difficult is because what you're suggesting, in fact, we've done research and actually use exactly what you're saying, having PV inverters actually generate a counter harmonic to actually limit to counter the background harmonic, is that there are all sorts of control issues and other issues, and there's gets to be interactions between the inverter controls and the system that can actually have a negative impact later on down things. So you might fix one thing but create another issue. So it's quite complex. That's all. I'll leave it at that.
Thank you, Professor.
Thank you, and thanks for the question.
No more questions coming through at the moment. We've got a pretty quiet audience.
Like I said, harmonics is really light in New Zealand. So,
so just to move on, yes, let's have some discussion, Professor Neville.
Yep.
Like I said, could you, with your experience, because you have been measuring harmonics and power quality across New Zealand for decades, and working with the utilities and industries, can you please give us a brief on how the industry has evolved by adopting the NZ-ECP when it was introduced in 1993, and then the introduction of AS/NZS 61000 in 2000, because I think I've seen your paper of how it will impact on New Zealand. And then later by 2012, we have PQ EEA guideline. So how is the industry evolving and adopting to these different standards and approaches? If you can please give us an insight, that will be quite helpful to move forward.
Oh, that's a very good question. Okay, so ECP 36, it actually is absolute. It was actually written when there was only a few well-known sources of harmonics, and the main ones were HVDC and the aluminium smelter. Now, if you read that carefully, actually the allocation of harmonics in that is only for 66 kV and above. And the levels for voltage actually at lower voltage are stipulated. They're all identical because they didn't know what to set. And actually there's no allocation method for lower voltage. So actually ECP 36 actually really only for allocation of harmonic currents, which are limiting harmonics, is only applicable at 66 kV and above. Now, along comes AS/NZS 61000 standards, which I'm actually part of the joint Australia-New Zealand committee adopting them. In New Zealand, they're actually only voluntary. So they only have to be applied when it's stipulated in something. And honestly, it hasn't really actually been adopted well at all in New Zealand. There's absolutely confusion. I get lots of questions from people in industry. Well, which one do I follow? So do I follow this or do I follow that? And I've actually seen ECP 36 misapplied in lots of cases because they have tried to apply the same thing and the same values at the lower voltage levels, which is not applicable to. So I would say AS/NZS 61000 hasn't been used very well at all, hasn't been adopted well at all in New Zealand. In terms of EEA power quality guidelines, a few utilities have adopted it and adopted it well. They actually put it in the connection codes. And so they say as part of your agreement for a connection, you agree to abide by this. I have gone around actually and done lots of measurements on different places and before and after changes to check whether it complies and help with mitigation. But that is only a few of the EDBs in New Zealand have actually taken that step. Now, the methodology in EEA Power Quality Guidelines was actually a simplified version of AS-NZS. It assumes you don't know the harmonic impedance of your system, so it uses some approximations to give it. So if you've got a computer model of your system and you can generate a harmonic impedance, there are other ways more accurate than that way. And the basic reason is most utilities didn't have a computer model of their low voltage network.
Got a couple of questions that have come through in the chat.
Yep.
So, question from Jackson White. I would be interested to hear Professor Watson's thoughts on the possible alternative approaches to limiting harmonic emissions.
Well, I guess at the first, it's always best to do it at the source. So if you can buy, get a device that is actually lower harmonic because of a better design, and a typical case was in the lighting area where you go to just a straight rectifier or a valley fill or what have you. For a small incremental increase in the price, you could get a better waveform, current waveform. But inevitably, the device was more expensive. The next step above that is on the bigger scale is diversity. And one of the things we've found working with utilities is they standardize. I like standardization, like 11 kV to 415 DYN 11 vector group. They will have thousands of them, and they've standardized every transformer between 11 kV and 415 of the same vector group. What we've found is actually if you actually use a few different vector groups, you can actually get very good cancellation in your lower. And we've got a EEA paper on this with Orion on using that in rural. So really good. The next step up is harmonic filters. Most people jump to harmonic filters. I would have to say it's a nearly a last-ditch effort because A, it increases your losses. B, it can add extra resonances to because your harmonic filter below a certain frequency capacitive, your network's inductive. There's going to be possible resonances and the standing losses. And then the next step is active harmonic filters. We've had a lot of actually work on active harmonic filters, which sound really great because they modulate and change to the changing loading condition. I would have to say they work when they're installed. They can cause quite a bit of problems due to tuning and other things further down the track. So it's not a, put it this way, it's not one of these things that you put in and leave and forget about. You actually need to check every couple of years that it's still actually working. And we've actually done that for one of the EDBs. We've actually did a check and found one of the ones they had in the system wasn't working as it should.
Fantastic, thank you, Professor Neville. And we've got another question here from Sorrel Peens. I hope I'm pronouncing your name right. How would harmonic filter banks be designed in a fast-moving industry with several renewable projects being planned to connect? Certain assumptions need to be made, but would be hard to predict which projects will actually reach financial close. So would need to guess how the wider industry would influence each grid connection. Let me know if you need me to reread that because I did not do a very good job on the first go.
Oh, probably if you could reread it and just see if I understand the question properly.
Yeah, sure. So how would harmonic filter banks be designed in a fast-moving industry with several renewable projects being planned to connect? Certain assumptions need to be made, but would be hard to predict which projects will actually reach financial close. So we would need to guess how the wider industry would influence each grid connection.
Yeah, okay, that's an interesting issue because it's indicating that the harmonic filters are sort of network filters, and we do have them. We've got one at North Makarira. But actually, typically, you would try and put the harmonic filter at the source, and you would actually try and make it so that actually the harmonics actually from that source will going into the harmonic filter and try and stop harmonics in the network going into the filter. So it needs a very careful design, but the basic premise is that if the project doesn't go ahead, the harmonic filter associated with it won't go ahead. If the project goes ahead, the harmonic filter for that project would go ahead. But I would actually, if it's a fast moving like solar farm or that, I would actually say the first step is to try and get diversity, so you'd limit how much harmonic filtering you actually need to do.
Great. Thank you. We've got a few questions rolling in now. So,
Yep.
Hi Neville from Josh Daly. I'm curious about the trend of EDBs replacing overhead lines with underground cables. How do you foresee the effects on harmonics and the overall system performance given the higher network capacities that will likely come from this?
Actually, a very good question, and I know I've been involved with Denmark. They've gone to underground and that, and actually it changes all the resonant points, makes it far more capacitive. Those resonance can cause problems, but the other thing it does do though is actually it reduces the propagation. So it actually acts as a nice filter. So basically, your higher frequency don't propagate as well as they do in an overhead system and your standing wave. So it actually can cause problems at lower orders, but actually helps you at the higher order harmonics.
Fantastic. We've got another question here from Ali Othman. Considering that voltage harmonics are primary concern for utilities to manage, should voltage harmonics limits be established specifically for utilities? On the other hand, given that customers have no control over network impedance, which can change during network restructuring or with the introduction of new loads or generations, would it be more appropriate to set limits solely on harmonic currents for customers?
Interesting question. It's a good one, Ali. Ultimately, it's a harmonic current that causes the distortion. And as you quite rightly say, the system impedance actually changes with time and configuration. So that is why IEC 61000 goes to a statistical evaluation procedure. And the reason for the statistical rather than absolute is to allow for the variation in actually the system impedance. So if you look at device limits, they're actually absolute. They're the current. So you basically say, I will put this device on a sinusoidal source. What is the current? Is it meet the device standard? But when it comes to the voltage limit, you look at the voltage harmonics and it will change over the time of day and week because the system's changing the number. And then that's why it goes to a statistical. And the whole purpose of that is to allow for that variation in the harmonic impedance of the network.
Fantastic. We've got a regulatory question here from Gerard. Hopefully I'm saying your name right, Jared. What are the EA's thoughts on enforcing existing connecting parties to remove background harmonics? Often an allocation request to Transpower at an existing GXP results in a small allocation as there is little headroom to the existing code levels.
Yeah, that's a good question, and that's what we're trying to determine through this consultation. Whether it's something gets mandated. If it's going to be mandated, it's going to take potentially a longer time because we work with other agencies, as we said. Or is it going to be an interim measure where we put something, guidelines in? So yeah, they're all options we are looking at. We are pretty open at this stage on whether it gets mandated or whether in the interim some guidelines are put in, or whether the EEA guidelines are used in some way. That's what we're doing.
Yeah, if I could just follow on with that. You see, the thing with that is that we talk about background harmonics, but the background harmonics is the distortion caused by other loads in other parts of the network. So if you take a whole system approach and everyone is within their allocation, you don't actually have an issue with background.
So what you're saying is the whole of system approach is really what we should be looking at.
Yes,
Which is
yes, and if we don't have enough headroom because the existing background harmonics are too high, we need to find out why they're too high and who's causing it to be too high.
Right. And that's exactly what we are discussing on the roles and responsibilities of who's going to take. Is it coming from the system operator or from the grid owner or from the network operators, distribution utilities? And because it flows down, whatever you have the headroom on the top, from the transmission it goes down to the distribution and then it goes down to the consumer level. So we need to have a whole of the system approach rather than a different codes across different regions.
Yep, that's correct.
And that measurement of harmonics will be key in that.
That's right, yes.
Yep.
Fantastic. Well, that looks like all the questions that we have today. So,
Okay. Do you have something else you want to probably have this discussion?
Yes. So there are a few other things that we would like to, especially for going forward with this thing. Like there were really good questions asking for mostly on the solar inverters, having standards for them. Like Professor said, there are two parts to it. The first is the connection part. You're connecting to your system operator, to your grid owner as transpower, or you're connecting to your utility. The second part is on the management of harmonics, because once it is connected, like we have been discussing, interaction of these solar farms or interaction between BESS and existing loads or the new data centers can actually shift your resonance, can change your impedances. The network impedance keeps changing. So we need to define the roles and responsibilities accordingly. And Professor Neville Watson, I have few things that will help the readers to understand and pose further questions on this, is that going forward, if there's any change in a particular standard or approach that we're going to choose, for example, if a utility is already using NZ-ECP 36, and if something they have to move towards 61,000, or if they have different approach, what will be the impact? What will be the impact on their approach? What will be the issues that they will be facing? What will be the technical difficulties or whatever it is that we can discuss?
Well, ECP 36 is actually quite conservative relative to AS/NZS 61,000. So I actually think that they will actually find it quite a bit easier. It would be harder to go the other way, actually. Yep. Yeah, the other thing with the going to AS/NZS 61,000, which is a mirror of IEC, is that the equipment we use for measuring is actually measures according to the European standard, which is basically set in the standards. So the good thing is we're not going to produce our own harmonic monitors in the foreseeable future. We're going to use ones and they will be compliant and designed around the European standards.
Oh, that's good to know, Professor. And because now with NZ-ECP 36, it sits because of the safety concerns, health and safety concerns. But now we are trying to move towards managing at the system operation level and ownership level. So how it will impact on the consumers, on the installers, and how difficult will it be for them to adopt to a new approach if we go forward?
I think at the moment there's a lot of confusion in the industry about which one applies, how to apply it, and what have you. So adopting one over the other is going to be a big step forward in terms of there's one point of source. This is what you have to comply with. Here's how you do it. And as I'm sure you know, the 61,000 is a whole suite of standards that is actually being developed over many years by lots of people in Europe. I think the only things that to be aware of with those is they are evolving over time. I know, for example, the measurement requirements are slightly changing over time. So we talk about harmonics being an integer of the fundamental. But we know that with all this battery storage systems, converters and that, and the way they switch, they're not actually in perfect synchronism with the grid at all times. There's higher frequencies, there's aliasing, there's picket fence effect. Because of the non-stationary nature of that, there is some spectral leakage. So instead of considering just they look at the sidebands. and they say those sideband energy is put into this one, and that's considered the harmonic. So at the moment, the new approach is they have 5 hertz spacing. So 250 is the 5th harmonic. So you take 245, 250, and 255 hertz signals from your spectrum, and you add them together, you combine them together, and that's your harmonic. And that's due to, so that's one of the changes happening. And the instruments, you don't have to worry about it. The instruments are automatically doing this.
That's good. That's good to know, because the other concern that people might have is, do we have those here in New Zealand if you're trying to adopt to a new one?
Yeah, yeah. The instruments already do it.
Fantastic.
Sure, Professor Neville. We have one more question from the audience, from Rob Orange. This is a 2-part question. So what guidance is available in New Zealand around measurements taken at the point of connection of a new generator? Their current emissions may be impacted by sinking background voltage harmonic distortion. And as a follow-up, generators with a collector network, a wind, solar, and to a lesser extent BESS, may resonate at certain frequencies which are more at risk of being assessed as non-compliant at those frequencies.
Okay, Rob, you picked up a few points. First of all, if you put filtering into a wind farm or solar farm, it can actually basically cause, sorry, they can cause harmonics from the network to flow into them, not just from the farm, which is true. That has to be carefully managed, but there's a bit more to it than that, because if there is 2 farms close together, they will actually affect each other's harmonic emissions. And so the real question is compliance with one running and the not, or is it have to be compliant? What happens if when you're 2 running, it's non-compliant? And I would say I'm a bit biased in this. I would say that we have to be careful of compliance by itself. We need equipment to be reasonably robust in terms of keeping the same harmonic current emission regardless of a certain amount of distortion on the voltage waveform, because you're in the system, you're never going to actually get perfect sine wave. So you don't want one that'll only comply if it's the only thing running in the system. You want something that'll actually run well and be a reasonably, if I'm allowed to use the word, resilient to a bit of distortion at the terminals. I've seen this in Australia, aluminium and a nickel plant. They had the same issue. The utility complained to one of them that they were non-compliant. They said it's because the distortion caused by our neighbours affecting our converters. Converter controllers is a big thing, because not only you mentioned moving resonant points, but they actually have what they call a control oscillation. They can have, because of distortion, they go into oscillation like that because of control modes in the time constants of the controllers. So one of the big areas in the future is going to be the design of the controllers for the converters to make them more robust to distortion and less likely to go into control oscillations. I hope that answers your question, Rob.
10:50. Any other questions? No more questions in the chat.
Okay. If I could just comment, one of the things I've noticed, if I'm allowed to add, is that manufacturers are basically trying to circumvent requirements by increasing the frequency. So as you mentioned, 2.5 kilohertz used to be what our ECP 36, as well as a lot of other jurisdictions. I found in the irrigation area that manufacturers are putting distortion at 4 and 6 kilohertz. I was helping a utility, and I contacted the manufacturer and I talked to them, and they have a switch. You could switch if you get interference on one, you move to the other, but it's still, they put it that because it's not regulated at the time. The next band that's gone up is to 9 kilohertz, and now they're talking about 150 kilohertz.
Wow.
EVs, some of the EVs, I won't name names, but they actually have distortion at 10 kilohertz. And that's because they get out of the 9 kilohertz band regulations. So I'm seeing more and more higher frequency switching speeds to push things out of the regulations to make it a bit easier.
I think there's a comment just on what you were talking about, Neville, about from Carl, talking about something about being pushed. I just
trying to get where that came from.
But agreeing with what you're saying,
Yes.
basically. People pushing it out just out of the band to
Yep.
Supplementing it, yes.
Yeah.
I have seen, from Carl, I have seen another very common inverter switching at 3 kilohertz just outside of the 2500
100 hertz.
hertz.
Yeah. Okay, there is one other thing I should mention. There's another technique that I have seen, and it's called a spread spectrum, and I really dislike it. And what a spread spectrum is, that they actually modulate the switching speed so that it spreads the distortion over lots of frequencies. And if you check it at any individual frequency, it's quite low, but the fact is it's blurred, it's smeared it over lots of frequencies. I have seen that actually in power electronics. Thankfully, not many manufacturers have picked up on that technique.
So just to follow up on that, Professor Neville, I think coming from policymaker kind of thoughts, what would be will the impact of having those harmonics at, let's say, 4 kilohertz or 9 kilohertz, same as your 3rd, 5th, and 7th order, which you're more concerned?
Yeah, good question. Okay, so the higher higher frequencies, they're actually lower impedance in capacitors, so they affect capacitors worse. They cause a lot more heating, because heating in transformers and windings are frequency dependent. So they're more detrimental. So definitely worse. But you get up to a higher frequency, and actually you'll find it's how would I put it? The higher frequencies actually affect immediately what's connected in the network, but doesn't go through the transformers. It may affect the transformers, but it doesn't affect the rest of the grid. So I've seen high frequencies in farms. They affect the farmer. They affect his network. Like induction cooktops are fairly sensitive. In fact, we've seen it when they couldn't use a cooktop when the irrigator's running, but turn it off and the cooktop would work. Things like that. But anyway, those harmonics get filtered by the transformer, so at the medium voltage, they're hardly perceptible.
Yeah, the low voltage and the consumers are more affected.
Yep.
Look, it's been really, really good. I'm sorry to interrupt, but we are actually running out of time. So I think this has been a brilliant discussion. Lots of really good questions. Thank you to the audience, and thank you very much, Professor, again, for being here to answer those questions. And Nasser, thanks for your presentation too. Have a good one, everybody. And just in case you aren't aware, we're also doing a webinar on Monday, the 8th of July, on the other 2 issues we're addressing. Thanks again, everybody, and have a wonderful day.
Thank you then. Take care. Cheers.
Thank you.
Thank you.